Let's go ahead and let's take a look at a couple of pretty easy problems and interpreting whether or not a set of numbers is a solution. So this would be problem number 7 and 8 in your notes. So if you look at this first problem, it says, is 1 comma negative 1 comma 2 a solution for the system? And it gives us all of the equations over here in that curly bracket. So all we're asking is if this particular x value and that y value and then a z value of 2 satisfy every single equation. And that would mean that this coordinate is at the intersection of these three different planes. And so it's just going to take a little bit of work to see if those numbers check out. So let's go ahead and let's make some space for the top equation. Okay, writing this out, I will have a space for x minus 2 times y plus 3z, and that should give us 9. We'll see if that checks. Put a little space there. So putting these numbers in, I will have 1 for x, negative 1 for y, and then 2 for z. Just doing some simple algebra, that says 1 plus 2 plus 6. And we are wondering if that's equal to 9. It looks like we are going to get 9 equals 9. So check. The first equation works, but we can't just assume that it's a solution. We have to check the other equations. So let's go ahead and let's do the middle one next. The middle equation has negative with the x value, plus 3 times y, and then plus z. And we should get negative 2 out of this. So let's put in those different numbers, 1, negative 1, and then positive 2. If we work out our algebra, that says 1 minus 3 plus 2 equals negative 2. If we have negative 4 plus 2, that indeed does add up to give us what we need. Okay, so we're looking pretty good. Top equation is satisfied by that point, and the middle equation is also satisfied by that point. But we can't get too hasty. We have to try the last one, and so this will be the bottom equation. If it fails here, it is not a solution. So we have 2 times x minus 5 times y plus 5 times z, and that equals 17. So putting in x as 1, y is negative 1, and then z is 2. Looks like we make 2 plus 5 plus 10 equals 17, and that in fact is 17 equals 17. Okay, so just showing a little bit of work and that those things are equal tells us that indeed the coordinate they gave us is a solution to this system. Now, it might not be the only solution. If we have infinite solutions, maybe this is just one of many points that actually satisfies it, but it at least is a solution. Let's go ahead and let's try number 8. 8 is the same idea. So we're given a new x and y and z values, and we have to put them into the different equations that are over there on the right. So let's go ahead and let's try the top equation. You don't have to go in order, but just seems to make sense to me. So we have 3 times x minus 5 times y plus z itself. We should be getting 25 out of this. So 2 is x, negative 3 is our y value, and then 4 is the z amount. 6 plus 15 plus 4 should give us 25. The 6 and the 4 make 10, and if we have 10 and 15, that indeed is 25. So it works with the top. That's good. Let's try the middle. Okay, looking at the middle equation, we have negative 4 times x, and then we are subtracting z, and we should get negative 14. So I just left kind of a big gap since y is missing, so that'll help me remember 2 goes here, but then we are subtracting 4. Y doesn't occur in that equation. So this makes negative 8 minus 4 equals negative 14. In fact, that is not true. Negative 12, the answer from the left, is not equal to negative 14. So this is actually one of those where it doesn't work. And if I fail the middle equation, that means this cannot be a solution. And so I don't actually need to do the bottom equation. You just have to find that it fails once, and that's it. And so we can kind of summarize. No, 2, comma, negative 3, comma, 4 is not a solution to that system. As we get better, we will be able to solve systems like this. There is a solution out there. This is just not the solution. It's a point that's not on all of the planes at the same time. Hopefully that makes sense, and it's actually not too hard. And although a lot of the work we will be doing isn't this simple, this is the concept behind the work that we're doing. So hopefully that makes sense. Let's go ahead and let's take a look at a couple of definitions and important terms. This is the first of a few different types of definitions. And so when we deal with matrices and we try to head towards the answer matrix, there are a couple of important steps along the way that get named. And so the first one, this is a very strange term, it's called row echelon form. Echelon just means like staircased or stepped form, row stepped form. And so what that is when a matrix has been manipulated to get the bottom left corner full of zeros. There will be numbers that kind of naturally occur along the diagonal. Okay, so that's kind of a general definition of what row echelon form is. I wanted to give you maybe a couple of examples over here in the space to the right. And so the first example is very small. It would say 4x plus 1y equals 24. 0x plus 1y equals 4. Notice there are zeros in this lower left-hand corner, and the diagonal of this left side is just full of numbers. And it doesn't really care about the upper right corner. It can be whatever. Another good example, this is a little bit larger one. It has a column for x's and y's and z's, but you'll notice this lower left-hand corner, again, is full of zeros. Everything else can be filled in with numbers. It's not a big deal. The last one is the biggest example, just so you can see this would have a variable for v and w and x and y and z. It has 5 different things that it's keeping track of. But this lower left-hand corner, as best as it can, is full of zeros. You will kind of notice we're not able to hold a perfect diagonal here, and that's because we actually have this extra column, and we don't have enough equations to really solve this. This is a problem that would be dependent on knowing a little bit more information before we could solve it. And that's a term you'll hear in a little bit. But after working out most of what we could, we got zeros in this lower corner, and everything else kind of along the diagonal here and there is a number. Okay, that's row echelon form. One silly thing about that matrix, I suppose, is that it just goes in order: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Then your answers go 13, 14, 15, and 16. So just something kind of weird. Now below, reduced row echelon form takes this a step further. Row echelon form has numbers in other positions where we don't necessarily want them. Reduced row echelon form finishes the job. And so reduced row echelon form is a row echelon matrix. Comes from this step where the leading entries are reduced down to 1. That's actually pretty important. That tells us the diagonal has been reduced down to 1. And then we use all those 1s to cancel out any extra terms. And what this does is this kind of creates our answer matrix. An answer matrix is called a reduced row echelon matrix. Here are a couple of examples that you could use. First example, having 1 along the diagonals, kind of a big deal. We would like to reduce those down to 1, and then we use the 1s to get zeros above them. So 1x equaling 5, and then 1y equaling 4. That's a reduced row echelon matrix. The second example would have ones along the diagonal, and we use the 1 here to cancel out things above it. We would use the 1 here to cancel out things above that, and we have our answer. 1x equals this, 1y equals that, and 1z equals 4. The last example of a bigger matrix, actually it's very similar to the matrix that we had up above. This would be kind of the answer matrix if you kept reducing, has 1s in those diagonal positions, or at least as close as we can get, and then you take the 1 that's here and you cancel out everything that's up above it. So using 1s to cancel out those, and using 1s to cancel out those, using this one to cancel out those. That's the goal behind reducing and putting it in reduced row echelon form. Notice the answers to that problem are pretty gnarly. That can happen a lot of times. And if you cannot get a perfect diagonal, you will often have these extra pieces hanging out in a column somewhere in your matrix. So a couple of important abbreviations as we see later in this target. Row echelon form is sometimes abbreviated as REF, and then reduced row echelon form is sometimes abbreviated as RREF. And those will show up later as I give you some shortcuts to solving these problems faster. Be on the lookout for those terms. I will try to use them as we solve our problems. But I hope you're starting to pick up on what solutions for matrices do and what the whole point of this target is. Basically to find a coordinate out in space, whether that's x, y, z, or even if it's got more letters than that. Finding all of those different variable amounts will basically be a big matrix with lots of zeros and a diagonal that's full of ones. Thanks for watching the video. I hope it helped, and we'll catch you guys in the next one. Bye.